Welcome back to Scrollopedia, and Happy New Year! We've explored TPU architecture, GPU infrastructure, even Apple's unified memory approach. But all those videos assume one thing, that AI needs specialized hardware. This video asks the more fundamental question: why? What is it about regular computers that makes them struggle with AI? We'll start with how traditional computers work, then explore what AI actually computes, and discover why the real bottleneck isn't processing power. It's something called the memory wall. By the end, you'll understand the core problem that every AI chip is trying to solve. Let's start from the beginning. Every computer follows the same basic design from 1945. The CPU is the brain. It makes decisions, runs programs, manages everything. Think of it like an expert chef who can cook any dish perfectly, but they work on one dish at a time. A modern CPU has 8 to 64 cores. Each core handles one task at a time, switching between them so fast you don't notice. This is called sequential processing. For 70 years, this worked brilliantly. Word processing, spreadsheets, web browsing, the CPU handles it all. The CPU is a generalist. It can do anything. For varied, unpredictable tasks, that's exactly what you want. But AI asks for something completely different. Here's what a neural network actually does. Every AI model is just a giant collection of numbers organized into tables called matrices. These numbers are the model's weights, learned during training. When you send a prompt to an LLM like GPT, Gemini, or Claude, your words get converted into numbers. Then something interesting happens. Each layer of the network looks for patterns in your input through matrix multiplication. The weights encode what patterns to look for. The multiplication checks if those patterns exist. The first layer detects basic relationships. The second layer combines those into phrases and meaning. The third layer recognizes context and intent. Layer after layer, the model builds understanding. Early layers see words, middle layers see ideas, final layers see what you're actually asking for. By the 100th layer, when you asked, "What is the capital of France?" the model has recognized enough patterns to predict the answer. The math itself is simple. Multiply numbers, add them up. But the scale is staggering. GPT-4 has an estimated 1.8 trillion parameters involved in every calculation. Here's the key insight. Unlike normal computing, AI does the same operation billions of times. That's what accelerators provide, thousands of cores doing identical work simultaneously. But there are actually two very different AI workloads. Let's look at training first. Training means teaching the model to recognize patterns. You show it an example, it makes a prediction. You tell it how wrong it was, it adjusts its weights slightly. Forward pass, backward pass, update weights, repeat, millions of times. Each pass touches every single weight in the model. For a 70 billion parameter model, that's 70 billion numbers processed for every training example. Why can't CPUs handle this? A high-end CPU has 64 cores. An NVIDIA H100 has 16,896 cores. That's 250 times more parallel processing power. Now you might wonder, what if we connected a bunch of CPUs together? The problem isn't just cores. A single H100 has 10 times the memory bandwidth of a high-end CPU, and connections between CPUs are 50 times slower than connections within a chip. You could connect 10 CPUs and still have less bandwidth than one accelerator. So training needs accelerators. But what about after the model is trained? Can't we just run it on a normal computer? Let's say you want to run Llama 70B. The model is trained, you just want to chat with it. Here's what happens when you type a question. Your input gets processed through the model, forward pass only. The model outputs one token, maybe the word "the." Then it runs again for the next token, capital. Then again, of. Then again, France. Every single token requires a complete forward pass through the entire model. Now here's the problem. Llama 70B has 70 billion parameters. That's 140 gigabytes of data. To generate one token, the accelerator reads 140 gigabytes from memory, does some math, outputs one word, then reads 140 gigabytes again for the next word. The NVIDIA H100 can do math at 2,000 teraflops, but its memory bandwidth is 3.35 terabytes per second. Reading 140 gigabytes takes about 42 milliseconds. The actual computation, about 0.07 milliseconds. Reading is 600 times slower than computing. The accelerator spends 99% of its time waiting for data. This is called being memory bound. The bottleneck isn't compute power, it's how fast you can feed data to the chip. Training is compute bound. Inference is memory bound. Different problems, but both need specialized hardware. And that memory bottleneck, it has a name. Here's a 30-year-old problem now defining computing's future. Every 2 years, compute performance roughly triples. Memory bandwidth only improves by 1.6 times. The gap compounds over time. In 2020, the NVIDIA A100 had 2 terabytes of bandwidth. In 2024, the B200 has 8 terabytes of bandwidth. And by 2026, AMD's MI400 promises nearly 20 terabytes of bandwidth, a massive leap. That sounds like massive progress, but compute is improving even faster. The gap keeps widening, not narrowing. This is the memory wall. We build faster processors, but we can't feed them data fast enough. Imagine a factory with 1,000 ultra-fast robots, but only one loading dock. The robots spend 90% of their time idle, waiting for parts. Building faster robots doesn't help. You need a wider loading dock. Every AI chip, from NVIDIA to AMD to Google to Apple, is fundamentally trying to solve this same problem. So why does AI need specialized hardware? It comes down to 3 things. First, AI is repetitive. Neural networks do the same matrix multiplication billions of times. Regular CPUs are generalists. Accelerators have thousands of cores built for this one job. Second, training and inference have different bottlenecks. Training is compute-bound, you need raw parallel power. Inference is memory-bound. The chip spends 99% of its time waiting for data. Third, the memory wall. Compute speeds grow faster than memory speeds. The gap keeps widening. Every AI chip is fundamentally trying to get data closer to computation. That's the core problem. If you found this helpful, subscribe to the channel for more deep dives into AI infrastructure and technology explained.